First of all, I would like to thank the SPP for organizing this wonderful online conference and also for giving me the opportunity to share with you our work on dynamical control of phases and time crystals in an atom cavity system. I had the wonderful pleasure of working with these fantastic people shown here. Together with Jim and Ludwig, we are responsible for the theoretical aspects of the project. Christoph, Fatamon, and Hans are all members of the experimental group led by Andreas. Okay, so in general, we are interested in answering this question of what happens when we shake a many-body system. And at least scientifically speaking, what we mean by shake here is we change a parameter, one of the system parameters periodically in time. So you have a well-defined frequency and well-defined modulation strength, if you like. So how strong you are driving the system. So in the field of periodically driven many-body systems, when you drive a system which hosts some type of equilibrium phase diagram shown here, so you have three competing or coexisting phases, phase A, B, and C. You can think of it as solid, liquid, gas if you like. What typically happens if you drive it are the following. So you have two possible scenarios. One, you either renormalize the phase boundary, meaning you expand or decrease the area in which a particular phase is stable. So for this specific example, you can see how the phase or phase B is now stable for a larger region in your parameter space. And then the other possibility is that you excite dynamical phases or non-equilibrium orders which don't have any equilibrium counterpart. So you need periodic driving, or at least you need some type of out of equilibrium scenario in order to excite such an order. So an example of phase boundary renormalization phenomenon is this light-induced superconductivity that was first discovered in the group of Andrea Cavalieri, also from Hamburg, where they found, or at least they look at this superconducting material LESCO, and they choose a particular doping and temperature where you don't expect to see superconductivity. So if you like, you are somewhere in this region of your phase phase diagram. I hope my cursor can be seen. Okay, great. It's good to know. And so in equilibrium, you don't expect to see any superconducting behavior. And what they did was to apply a pump pulse. So basically drive the system, shine light on the sample. And to their surprise, they were able to see transient superconducting behavior. So in a way, you basically increase the regions or the region of stability of your superconducting order. So this is an example of phase boundary renormalization. And as for the second scenario, which is the emergence of non-equilibrium order, the most recent example is this new dynamical phase of matter called time crystals. And the way to understand time crystals is by comparing it with what we know and love, a solid state crystal, a typical solid, if you like. So in a typical solid, we know that its characteristic feature is having a periodic pattern in space. So, I mean, mathematically speaking, it breaks space translation symmetry, right? So it self-organizes at specific points in space. And in the absence of external factors or coupling to the environment, you don't really expect to see your solid to change over time. So in contrast to this, a time crystal has both periodic patterns in space and also in time. So you self-organize in space, and also you also have a certain periodicity in time. So the system is dynamical, it moves over time. So you can imagine applying a periodic drive in the system. So it has a characteristic period capital T, for example. And the time crystal will instead oscillate at integer multiples of the drive more than integer multiples more than 1. So meaning you can have 2t time crystal as shown here. So it will only go back to its initial configuration after 2 driving cycles. You can also have 3t, 4t, etc., etc. But the point here is that you are breaking space and time translation symmetry. And indeed, this time crystal phenomenon was first observed not so long ago, 2017, in 2 different experimental groups, one in the group of Chris Monroe using an ion chain trap, and also from the group of Misha Luken using an NV Senta diamond. So the question that we are concerned with, a specific question that we are concerned with is, can we observe this dynamical phenomena, namely this renormalization of the phase boundary and also the emergence of the dynamical order using a single platform. So far, the examples that I've given, you basically you have two distinct examples, right? One for superconductors, and then the other using essentially cold atoms type of system. So more specifically, is it possible for a platform to basically have one tuning knob? So for example, the driving strength or the modulation strength. And just by increasing it, just by changing it, you go from renormalization of the phase boundary to emergence of non-equilibrium order. And to answer this question, we look at the specific cold atomic platform, which is this atom cavity system. So it consists of a Bose-Einstein condensate, BEC, inside a single mode optical cavity. We are pumping photons from the side. So we have this transverse pump laser here, perpendicular to the cavity axis. And what it does is that it provides photons into the system. And in principle, that photon or those photons can be scattered in all directions. And because we have initially a homogeneous distribution of a BEC, so you have a homogeneous distribution of atoms, so actually scattering into the cavity, so directly at the perpendicular direction, is highly suppressed because of destructive interference. So this system is a driven dissipative system. So there are photons leaking out of the cavity. So it's an open quantum system, if you like. And experimentally, what it does is that it provides, you can imagine putting a photodetector here or there, and you can use this information to observe in real time what's going on in the system. Okay, so this is the platform that we're interested in. And even without periodic driving, the system itself is already interesting by itself. So if you simply just increase the pump intensity, so again, this is just the intensity of this transverse pump laser here. So, I mean, if you like, you put more photons into the system. And then if you look at the number of photons inside the cavity, uh, for low values of pump intensity, the stable configuration is a homogeneous distribution of the BEC. Stable meaning it's a steady state or ground state, if you like. And so because of its homogeneous distribution, as I've said before, scattering into the cavity is suppressed due to destructive interference. But at some point, as you increase the pump intensity, it becomes energetically favorable for the system to start scattering photons into the cavity, okay? And this can only happen if somehow your atoms self-organize in a checkerboard pattern. So now you can imagine if it self-organizes in a checkerboard pattern, essentially what you have is a Bragg experiment. So you have this Bragg grating, it has this checkerboard pattern, and it satisfies the correct Bragg condition for scattering photons on the perpendicular or on the transverse axis and into the cavity axis. So if you look at the number of photons as a function of the pump intensity, as you increase the pump intensity, eventually you will start seeing photons into the cavity. And this is the main distinguishing feature between a homogeneous BEC phase on one side of the transition and a density wave phase on the other side of the transition. So from the perspective of the atoms, you can cook up an order parameter, just like you always do, to distinguish between two different phases of matter. So on one side of the transition, you have a homogeneous distribution. The phase or the order parameter corresponding to the density wave pattern is 0. And then on the other side of the transition, you get these two possible values. So you either get a positive or a negative order parameter corresponding to whether you have an odd or an even checkerboard. So you can imagine having a chessboard, you have black tiles and white tiles, and the system will spontaneously pick one of the two possible checkerboard pattern. So in this way, it breaks Z2 symmetry. Okay, so that is without periodic driving. So now let's shake the system, and specifically, let's periodically drive the pump intensity. So on the left here is the dynamical phase diagram that we obtained by looking at the long time behavior of the system. So we look at the number of photons inside the cavity after some after some driving cycles. So we look at the steady state regime. And constructing it is relatively straightforward. So if there are photons inside the cavity, that means you are in the density wave phase. You have a Bragg grating. You have this density wave pattern that allows for scattering photons into the cavity. On the other hand, if there are no photons in the cavity, that means you are in the homogeneous BEC phase. Okay? So on the y-axis, we have the pump intensity. And on the x-axis, we have the relative driving strength. So without driving, so these are in units of, or the pump intensity is in units of the critical pump strength required to enter the density wave phase. Okay? So as you increase the relative driving strength, what you see here is that you stabilize the BEC phase more. So for example, at this point here in your phase diagram, in equilibrium, you expect to see a density wave phase, but because of the driving, you basically extend the region where you see the BEC phase in your phase diagram. And shown here on the right is a short clip of typical numerical results that we obtain. This is a mean field simulation of this atom cavity system. And the main control knob, so the main thing that we are changing is the pump strength. And we are interested in how the system reacts to this change. So specifically, we look at the number of photons inside the cavity. So here we are linearly increasing the pump intensity. So what we're trying to do here is that we're trying to mimic what can be done in the experiment. So we are linearly increasing the pump strength or the pump intensity, and you see that the number of photons inside the cavity as shown in this panel is still 0. So that means we are still in the BEC phase. So we linearly increase it, and then around 5 milliseconds, we're going to keep it constant. So we have reached the desired value of the pump intensity that we want. So for example, 1.03, I mean, in this phase diagram, right? Okay, we keep it constant, and we allow the system to react to this change and to relax to a steady state. So we keep it constant for 5 milliseconds, and we see that for this value of the pump intensity, it turns out that the pump strength is already beyond the critical value required to enter the self-organized density wave phase. So you start scattering photons into the cavity. That means if you look at the atoms, they are already in one of the two possible checkerboard patterns. And then after 10 milliseconds, we will switch on the driving. And what you saw there is when we switch on the driving, you see that the number of photons inside the cavity decreased. That means we go back to the BEC phase. So we look at this for different combinations of pump intensity and relative driving strength, and this is how we construct this phase diagram. Okay, so this is our theoretical prediction, and we were fortunate enough to be collaborating with experimentalists who are willing to listen to our ramblings and to our suggestions, and they verified this in the experiment done in the group of Andreas Emmerich. So you can see here on the right panel the color plot for number of photons inside the cavity on the z-axis. Y-axis you have the modulation strength, on the x-axis you have time. And as you increase the modulation strength, you suppress more photons inside the cavity. Okay. So now what
Jason,
happens?
You have 1 minute.
1 minute. Okay, I have to hurry up then. So now what happens when we simply increase the modulation strength? So if we increase the modulation strength, we access this new. We access this. We saw this emergence of a discrete time crystal, and what it looks like is the following. So here we look at the long time behavior of the system. So again, the pump intensity is the thing that we are changing over time. In the cavity, you see that it's just pulsating. It's, at least from the cavity's perspective, it looks like it's just following the dynamics of the periodic drive. But if you look at the single particle density, essentially the atomic distribution, what you see is something else. So you start with an odd checkerboard. After one driving cycle, you go to an even checkerboard, and only after the second driving cycle that you go back to the odd checkerboard. So here you have you basically broke space and time translation symmetry. So you have a period doubling solution of the system. And these are just preliminary experimental data. So the pulsating, so the orange curve corresponds to the number of photons inside the cavity. You see this pulsating behavior, as I've shown before. It follows the period of the drive. But if you look at the relative phase between the cavity and the pump field, which essentially tells you whether you are in the odd or even checkerboard, you see a period doubling instead. So just to summarize, so we went out to basically look for a platform where you can realize both dynamical phenomena, namely the renormalization of phase boundary and the emergence of non-equilibrium order, specifically a time crystal. And we were able to show that for an atom cavity system, you can indeed realize both by simply increasing the relative driving strength. So thank you everyone for your attention.
Good morning. I am here to present our work on behalf of my co-author, Alfredo Coro, titled Desorption Kinetics of Bismuth Adsorption in Nickel 100 Revealed through temperature program spectrum, a kinetic Monte Carlo study. We are from the Institute of the Mathematical Sciences and Physics at UP Los Baños. In this presentation, we're going to talk about how a kinetic Monte Carlo approach can be used to reveal the identity of the desorbing species during temperature program desorption of bismuth on nickel 100, and also answer the question on whether atoms and dimers can coexist on the nickel 100 surface. Because if they do, then the desorption kinetics is best described as both first order and second order. It is also reasonable to ask, what imprints, if any, will they leave on the temperature program spectrum? Numerous studies has applied temperature program desorption, or TPD, technique, also known as temperature desorption spectroscopy, TDS, to the bismuth on nickel 100 surface. In this surface probing technique, a sample, which is bismuth in this case, is mounted on some surface, which is nickel 100, at some initial temperature, and is heated gradually so that the temperature rises linearly. A mass spectrometer is placed nearby to measure the flux of the desorbing species. These detailed measurements are represented by TPD curves. Of all the numerous TPD studies, we are interested in two of those in particular. The first one is by Jones et al. This one is published in JVSTA in 1990. And the second one is a follow-up paper in 2000 by essentially the same group, but with Panha as the lead author. This paper appeared in the journal JPhysChem. In this slide, Panha et al. Plotted a TPD spectrum showing the amount of desorbed species as the temperature increases starting at 600 K. Here we are particularly interested in the portion of the spectrum above 1000 K. In this temperature regime, there are clearly two peaks, but the low temperature one is apparent only on the two topmost curves. These represent initial bismuth coverages of 0.96 monolayer and 1 monolayer. Another feature of the desorption spectra is that the curve widens or broadens as the initial coverage increases, and in fact, as mentioned previously, terminates in a sharp peak at 1040 K. Finally, we observe that the primary peak shifts towards lower temperature with increasing coverage. How did these two studies explain these peaks? Basically, they propose that the primary peaks are due to desorbing bismuth atoms, while the second peak, which appears at only high initial bismuth coverages, can be attributed to a repulsive lateral interaction among the add species. However, Jones et al. And Panha et al. Could not rule out entirely the possibility that dimers may account for some of these peaks. The reason is rather technical. The maximum mass measurable by the mass spectrometer that is used to detect and measure the flux of desorbing species is limited to 300 AMU, or atomic mass unit, well below the mass of bismuth dimer ions, which is 418 AMU. Can we resolve this issue by using a kinetic Monte Carlo approach? First, let us summarize its attributes. Number one, we know that it is some kind of coarse-grained molecular dynamics simulation, thus able to simulate far longer times, the order of microseconds and seconds to seconds. Number two, that it can simulate true evolution of the dynamical system. Number three, that each kinetic Monte Carlo step can be mapped out or mapped onto a physical time, unlike equilibrium Monte Carlo. Number four, that it's able to deal with non-equilibrium process. In other words, it seems appropriate for the problem at hand. Atomistic lattice gas model features and input parameters. Random absorption. During the deposition phase of the simulation, bismuth atoms with the gas phase adsorbs unoccupied fourfold hollow sites. This process is not thermally activated. Diffusion. A bismuth atom undergoes long-range diffusive hopping by jumping from site to site. The actual activation barrier that must be overcome takes into account the number of nearest neighbors that it interacts with via repulsive lateral interaction, typically of the order of 0.1 electron volt. Dimerization. It involves two nearest neighbor bismuth atoms forming a dimer. An activation barrier erect is imposed to execute this move. Dissociation, a bismuth dimer breaks up into two adjacent bismuth add atoms. This is an inverse process to dimerization. An activation barrier EDIS is imposed to execute this move. Desorption, bismuth atoms or dimers leaves the surface to join the gas phase after overcoming a barrier, EDIS. Games and model implementation. Simulation details. Initial temperature is 900 K, lattice size is 100 by 100, heating rate is 5 Kelvin per second. Each data point is a result of 200 trials. 3 models are created. Model A, only add atoms exist, dimerization is suppressed. Add atoms interact via repulsive lateral interaction. Model B, minimal dimerization resulting in the coexistence between bismuth atoms and considerably less dimers, as species interact via repulsive lateral interaction. Model C, significant dimerization resulting in surface being predominantly populated by dimers above 0.2 monolayer coverage. No lateral interaction is imposed. And here are the results of the simulation. Model A, Model B, Model C. Note that of the three, Model A best resembles the features of the experimentally obtained TBD spectra shown earlier. Although Model B, the one where minimal dimerization is allowed, is also a good match to the experiment, though the secondary peak is taller than the primary peak, contrary to experiment. Finally, I thought I'll show you what will happen if you vary the lateral interaction, ranging from repulsive to neutral, then attractive. Here, the parameters are in line with Model A. As we can see, the best match to the experiment is one in which there is a repulsive interaction 108, as shown by the green symbol. To summarize, we have demonstrated using appropriate KMC models that the presence of dimers is not just inconsistent with the experimental TPD profiles. However, their numbers, if they exist, cannot exceed a threshold amount. The best fit model is one in which the sole desorbing species is the add atom, and whose desorption rate is influenced by a repulsive lateral interaction. In other words, we have shown that the desorption kinetics on bismuth on nickel 100 is predominantly first order. Thank you.
So good morning, I'm Vladimir Villegas. I'm a PhD student of Dr. Christine Villagonzalo, and I will be talking about the free energy in the spin transport among particles in a Fermi-Hubbard optical lattice. So this is the outline of my talk. So in the very first place, we make an optical lattice by trapping the particles of a Fermi gas using counter-propagating laser beams in 3 dimensions, and we remove the higher energy level particles using evaporative cooling. Once the particles are trapped in the optical lattice arrangement, their dynamics are then described by the Fermi-Hubbard model, which can be used to study the conductivity spectrum of a harmonic potential, the doping of an antiferromagnet, and the charge transport complication among lithium-6 atoms. But in this study, we would want to know what is the free energy for each lattice site in a spin transport for a Fermi-Hubbard optical lattice that is due to its interaction with the Fermi gas bath. So in the very first place, the dynamics of the particles in a Fermi-Hubbard optical lattice is summarized by the Hamiltonian in equation number 1, wherein your particles are then trapped by a Rabi laser that produces a Zeeman magnetic field, giving an energy delta sub r, and providing a separation among the spin up and the spin down particles. And then those particles can then tunnel to the nearest neighboring site with an energy J. The particles in the site can also flip their spin because of the Raman laser energy that gives an abelian magnetic field, giving an energy of omega sub r. And if there are two particles in a lattice, then their interaction is then characterized by the antiferromagnetic energy U. And the Hamiltonian is expressed in terms of your annihilation operators for a particular spin sigma on the optical lattice site J. The particles in the optical lattice site have dynamics that can also be expressed in terms of the annihilation operators and the Vanier functions given by equation number 2. Now, suppose that this Fermi-Hubbard optical lattice interacts with a bath that is described by Fermi gas Hamiltonian in equation number 3, wherein C is the spin of the particles and the Kth energy level. This Fermi gas is also described by the bath field operator given by equation number 4, for which rho is the density of your bath and V is the volume of it. Now suppose that in this interacting system, only one energy level of the bath is accessible. That is only, and the rest of the particles in the bath are belonging to a field. This then enables us to know what are the resonant energies in the bath that enable the driving of the optical lattice particles to a spin transport. This interaction is then described by the Hamiltonian in equation number 5, which is in terms of your uh, field operators, and alpha sub I is your scattering length due to the interaction. Mu is the reduced mass of the bath and the system combined. Now, at zero temperature and in equilibrium, remember that the interaction has a unitary time evolution given by equation number 6. And if we perform this unitary time evolution, we then see that there are 3 processes that the bath can drive your system into. Either a spin transport into the nearest neighboring site, a spin flipping in the same site, or while spin transport is being conducted onto the nearest neighboring site, the spin of the particle can also flip. There are 2 particular methods for which you can tackle these kinds of systems. If you want to study more of the diffusive properties, you use the Born-Markov master equation. Or if you want to take into account the strong interactions, you use the coherent state path integral. And in this study, we use the second method, for which you then characterize your temperature as an imaginary time, and then take in the Hamiltonian that we have a while ago, we promote the annihilation and creation operators into Grassmann variables, for which we can derive the action in equation number 7. And after taking the sum over all the possible paths, we then obtain the partition function, which gives us all the needed information about our system. Take note into account, however, that in this system, we are at zero temperature and only a transport of the particular spin to the nearest neighbor is taken into account. The rest of the 2 processes we then ignore. Now, if we study the spin transport, we then observe that there are 5 energy level scenarios in the bath that can enable the driving of a spin transport in your optical lattice. And if you see here, they are just expressed in terms of the energy due to the Zeeman magnetic field, the delta R, and should there be particles of different spin in the lattice site, it can be also expressed in terms of the 2 particle interaction U. And then we can also derive the free energy for each lattice site, which is a thermodynamic variable that gives us a lot of further information, such as entropy, the chemical potential, etc. And for each lattice site, the free energy is given by equation number 9. And this has 2 particular scenarios wherein either your lattice site is full, for which the free energy is indeterminate, or rather the lattice site is empty, for which the free energy is indeterminate, or that your lattice site is full, meaning there is a spin up and a spin down particle at the same time, and the free energy would then approach 0. So for the conclusion of my study, we did this for a Fermi-Hubbard optical lattice that interacts with a Fermi gas bath, and we observed that there are 5 energy scenarios in the bath, for which it needs to be resonant in order to induce spin transport among optical particles in the optical lattice site. And then it is in terms of the Zeeman magnetic field and or the two particle interaction. And that for the free energy for each lattice site, only a spin up and a spin down transport is either indeterminate for an empty lattice site or zero for a full lattice site. For further studies, I plan to conduct by deriving the conductivity and the other thermodynamic properties of this system.